All right, let's continue our discussion of logarithms with section 6.2, properties of logarithms. So this is just going to be a series of relatively simple rules. So the exercises are going to be applications of these simple rules. There's going to be more applications than normal. So we got more exercises than normal. 13, 23, 25, 31, and 33. And this is just going to be logarithm laws. That's what we're going to work on. And I would ask that you work through examples 1 through 3 in the book. So getting right into it, again, the whole thing is going to be the log laws, or the blah blah blahs, log laws. If you're a fan of Arrested Development, you might recall the blah 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 law blog. And I don't know how many of you have seen that show. It's getting older, but pretty fun little show. So the log laws are going to have real numbers a, u, and w positive. So again, by writing the number as positive, I'm indicating it's a real number and it's positive. And then the real number c, which might not be positive. Okay. So the first log law is that the log base a of u times w is equal to the log base a of u plus the log base a of w. And the second logarithm law is that the log base a of u divided by w is the log base a of u minus the log base a of w. Third log law is that the log base a of, now inside the parentheses, I've got u to the c, is equal to c times the log base a of u. Now what I've done is I've taken the power and pulled it out of the logarithm. Since I'm dealing with the exponent or a power, this is sometimes called the power rule, but there are plenty of other rules called power rules. So if you just hear the power rule, it could mean any number of things. But that's what we're going to call the power rule for this class. We also have that log base a of u is equal to log base w of u over log base w of a. And again, these are not my favorite letters for this, but these are the letters that the book chose. And I want you to see the a is on the bottom here, so the a is on the bottom here. The u is on the top here, so the u is on the top here. And these two, it doesn't matter what they are, they just need to match. So we've gotten a log base a with some formula involving log base w, so we've changed the base, and for that reason this is called the change of base formula. All right, so I don't want to prove these for you in any careful sense, but let's just go through an example of number 1. So I'm going to write log base 2 of 32 is equal to log base 2 of, and I'm going to write it like this, 4 times 8. Okay, and that's not confusing to anyone because 32 is 4 times 8. Hopefully that's not confusing to anyone. So now, how do I convince you that this is actually equal to log base 2 of 4 plus the log base 2 of 8? And, one way to see this is that 32 is 2 to the 5th, and this is equal to 2 to the 2 plus 3. So this is, 2 squared times 2 cubed. So when I'm looking at the product of these two powers of 2, that's the same as looking at the logarithm of this one and adding it to the logarithm of this one. So see how the exponents add here because I'm multiplying the two numbers together. So again, this is certainly not a proof, as it were, but I just wanted to kind of indicate to you an example of the first law working. The other laws work for similar reasons. So, again, u times u would give us 2 log u, etc. And we don't really need to worry about proving these so much as I want you to be familiar with them. Also notice if we can multiply, we can divide. These are real numbers, they're positive. We're not worried about dividing by 0 or anything. So here's the kind of question that I'm going to ask you to do. So write the following in terms of log x, log y, and log z. All right, and I'm going to give you log of x squared times y to the 5/3. I'm actually going to make this a little bit larger. We've got the log of, there's a big fraction here, x squared y to the 5/3 over z. So the way I'm going to do this, I'm going to write log x squared y to the 5/3 over z. Well, this is the log of the top divided by the bottom. So I'm going to write this as using rule 2. And you don't have to indicate that you're using rule 2. I'm just doing it so that as you look back over your notes, you can see what happened here. I've got the log of the top thing, which is x squared y to the 5/3. Oops. Minus the log of the bottom thing, log of z. And so we've got a log z now out of this mess, but we're not done. We've still got some other stuff we need to pull out. All right, let's continue. Well, this is the log of one thing times another thing. So using rule 1, I can write this as log x squared plus log y to the 5/3 minus log z. And sometimes, so I'm going to put the parentheses here, but sometimes if I've just got a variable by itself, I'll forget the parentheses, and that's okay. And now I want to finish by using the power rule, and I'm going to do that by pulling out these exponents. So we see I've got the exponent on the inside, so I can pull it out. Exponent on the inside, I can pull it out. So this becomes 2 log x plus 5/3 log y minus log z. See, I already stopped writing the parentheses. Now, this was y to the 5/3. This 5/3 got a little bit large here. Let me maybe make that a little bit clearer. This is y to the power 5/3 happening here, not y times 5/3. Now, real quick check. I've been writing log, 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 log. What is the base of this logarithm? Okay, remember log of x is log base 10 of x if it's not specified otherwise. This is what we call the common log. Okay, let's do another type of example. So this was taking a big nasty single logarithm and writing it into a bunch of component logarithms. So now let's do the opposite of that. Let's write as a single logarithm so what are we writing as a single logarithm? I've got 1/2 ln z plus 1 minus 2 ln x minus ln y. All right, so solution. We're going to do the exact same thing now, but backwards. So I write down the problem first. 1/2 natural log of z plus 1. That's what ln means. 2 natural log of x minus natural log of y. Now, there's not like a single correct way to do this. There's not a single correct order, but I'm going to kind of try to put things in an order that makes sense to me. So I'm first going to try to, since I've got some subtraction here, I'm going to try to put things as either plus or minus. And this minus minus can be a little bit confusing. So for me, it's easiest to leave the first term alone, natural log z plus 1, and I'm going to put these next two together as minus 2 natural log x minus natural log y. Now for you, this might not be the simplest first move. Oh, sorry, plus. That's the whole reason I did this. But because I'm going to be worried about these minus signs, I want to make sure that I've got my pluses and my minuses. So all these negative things I'm grouping together, and everything else I'm grouping together. So now I'm going to apply the power rule. And the way I'm going to do that is I'm going to turn this into an exponent of the inside, and I'm going to turn this into an exponent of the inside. And now I'll have natural log of the square root of z plus 1. And if that square root was a bit of a record scratch for you, square root, it's because, you know, z plus 1 raised to the quantity 1/2 is the square root of the quantity z plus 1. Now minus, keeping everything organized, natural log of x squared. Again, the 2 is coming inside of the parentheses there. So it's not the natural log of x and then we square it. It's the natural log of the quantity, which is x squared. Natural log of y. All right, now I've got a sum of logarithms. And remember, I can write a sum of logarithms as a logarithm of a product. So using rule 1, I've got the natural log of the square root of z plus 1 minus the natural log of now the logarithm of that product, x squared y. And finally, I can finish with rule 2 since I've got a subtraction here. And I've got the natural log of, on the top I've got square root of z plus 1, and on the bottom I've got x squared y. And that's my final answer. Okay, so I hope you're seeing that this is not a spectacularly difficult thing. Certainly if you're not familiar with the rules, you know, and I'm moving a little quickly, that can be a little bit difficult, but after you become familiar with these rules and you rewatch this video, hopefully you'll see like, oh, he's really just using these same 4 rules over and over and over again. Well, really, I've just been using the first 3 over and over. So that portends, of course, let's use the 4th rule. So write log base 19 of 73 in terms of ln. So solution, I'm going to write log base 19 of 73 because Pink Floyd's Dark Side of the Moon came out in 1973, fantastic album. But I need to write it in terms of natural log. So I need the base of, I need to use this rule number 4 here. Whoops, almost erased it. So I need the base to match top and bottom, which means I'm going to have natural log on top and bottom. And the old base goes to the denominator, and the old input to the logarithm becomes the numerator, the input for the numerator. So I've got now natural log of 73 over natural log of 19, and that's really it. But sometimes, so that's really it. We just applied rule 4. That's the whole exercise. And if that's a little anticlimactic, like, wait, but is there something else? No, there's nothing else. But the reason this thing is so important is if you look at a calculator, and like we've revealed in previous videos, I don't actually have a calculator on this iPad, but if we look at a calculator, how do I do input? There we go. We don't have a lot of logarithms. We've only got a few logarithms. Apparently I don't know where the logarithms are here. Discrete math, functions, and calculus. Let's just see if there's some. I'm not seeing logarithms. Well, anyways, if you were to look at your calculator, you're going to notice that it doesn't have logarithms. Or it doesn't have all the logarithms. It's, oh, here we go. We've got log base 10, we've got ln, and then, oh, this is nice. I guess GeoGebra has a log base whatever. Well, that's handy for them. But on your calculator, you're going to notice that you don't have one of these keys. And in order to calculate logarithms of other bases, you're going to need this change of base formula. It's really simple, and it's really handy if you ever need to compute things, especially log 2. Like if you have a calculator like on your, you know, I don't know how the Android phones are, but for sure on my iPhone, I don't have a log base 2 button. If you rotate it to the side, I've got natural log, which is log base E, which is roughly 2, but not quite. It's just 2.718281828459045 ... And I've got log base 10, But I quite frequently need to compute log base 2 if I'm doing computer science stuff. So I can always get an exact estimate by doing natural log of whatever I need to compute divided by natural log of 2. Well, let's just do a quick example of that. Compute log base 2 of 4,987. Okay. So solution. The log base 2 of 4,987 is going to be natural log of 4,987 over the natural log of 2. And natural log isn't special. This is correct, but I could also do log of 4,987 divided by log of 2, or any other logarithm I want, just so long as the logs, the bases of those two logs match. The bases of those two logs match. Okay, hopefully you can practice this a little bit, and really, if these seem a little confusing at first, just play with it some more, and remember this little example here, and hopefully after going through these exercises, this will make sense to you. It's just a new set of rules to learn. All right, best of luck.